All right, so the last differentiation technique we need to look at is what we call implicit differentiation. So we know that equations, exactly what they've got, equation like x squared plus y squared, we know that they're related to each other. Neither one of them's a constant. So typically what we've done in the past is rearrange our equation and got y equals, okay? What you can in fact do is differentiate each term with respect to x. So what my implicit differentiation process tells us to do is differentiate each term with respect to x, and then we still have equality, okay? So the derivative of x squared with respect to x is something we've always done. That's just 2x. Now, the derivative of y with respect to x is a chain rule. And so what we're going to do is we're going to work out the derivative of y squared with respect to y and then multiply by the derivative of y with respect to x. And that gives me the dy squared dx that I'm looking for. So in fact, what we do, and whenever we see a y expression, we differentiate that y expression with respect to y, and then in reality multiply by dy dx. So the derivative of y squared with respect to x is 2y times dy dx. And the derivative of 1 is a constant, so that would be equal to 0. I'll squeeze that in. So then we can say negative 2x is equal to 2y dy dx, divide by 2y, we get negative x on y equals dy dx. So the biggest difference is our derivative is often in terms of x and y. Okay, so if we go to these examples that we had here, the derivative of find dy dx in each of the following. So the derivative of x cubed with respect to x is just the derivative of x cubed with respect to x is just 3x squared. Derivative of y squared with respect to x is derivative of y squared with respect to y times dy dx. Yeah? And so we've got our 3x squared there. The derivative of y squared with respect to y is 2y times dy dx. And there's my dy dx expression. Now we divide the 2y across and we get 3x squared on 2y. Now, believe it or not, that's an equivalent expression. I could have taken the square root of x cubed, y is equal to that, plus or minus, and differentiated and got a similar answer. Okay, but it's just tidier this way. Example B, same process, except this time I've got a product rule. I've got two different functions there, so it's got to be the derivative of the first times the second plus derivative of the second times the first. So the derivative of x, so the derivative of x is 1 times the second function plus the derivative of the second function, which is just y, which is dy dy, which is 1 times dy dx, times the first is equal to, well, the derivative of 2x is just 2 and derivative of 1 is 0. Okay, so now I get y plus x dy dx equals 2. Take the y across, I get 2 minus y. Divide by x, I get 2 minus y on x. X squared plus y squared equal to 1, which is pretty much what I just did there before. Derivative of x squared with respect to x is 2x. The derivative of 2y with respect to x, well, it's dy squared dy. So derivative of y squared with respect to y, which is 2y, times dy dx. And we take our 2x across, divide by 2y, we get our minus x on y. And you can see the cas dump there. The order is important. If x cubed is equal to y squared, I implicitly differentiate x comma y, 3x squared on 2y, which is what we're looking for. If I put y comma x, I get 2y on 3x squared, which is obviously a different answer. So one's One's dx dy, the other is dy dx, isn't it? Because it's the reciprocal of each other. Okay? So order is important, whether it's dy dx or dx dy you're looking for. Hang on, we must have another question down here, have we?